So we initially detect, the sensory information that is electromagnetic radiation within the range of visible light with specialized cells. They're called photoreceptors, and I've got one under construction here, actually, that are located. They actually go in like this towards the back of the eyeball in an area called the retina, which is the layer of multiple cells. But the very structure of our eyes is actually really important for allowing for detection of visual information. There's a number of important components of an eyeball. And it helps actually for depth perception, for comparison, of inputs. To have two eyes actually, we're actually kind of interesting. We have two eyes in the front of our face, right? So we could actually have those inputs kind of converge and allow for extraction of information regarding depth. Prey animals often have eyes on either side, right? So they can sort of scan a broader range. But we like to converge and be able to see things and know precisely how far away they actually happen to be. So reflected electromagnetic radiation within the range of visible light, which is coming from objects, will strike first a clear kind of component of the eye called the cornea. And the cornea, has no blood vessels, that flow through it. There's a humor behind the cornea, which contains, chemical nutrition for those cells. But the cornea does have quite a number of specialized sensory neurons. They're called nociceptors, and they bind chemicals that are released from damaged cells. So they detect injury. And if anybody's ever had a scratch on their cornea, what they call a corneal abrasion, it's a memorable experience because there's a very powerful activation of those nociceptors. And that gets mapped, and people kind of very viscerally experience that searing sort of pain. So the cornea, there's good reasons why. If you scratch your cornea or abrade your cornea, that there's going to be, it'll be a very salient, kind of emotional stimulus as a result. Light will pass through the cornea, though, pass through that humor, that fluid behind it, and then enter into this hole that we call the pupil. And there is a pigmented structure that's called the iris, which is named after the Greek goddess of the rainbow, that is attached to muscles, and it can determine how much light can enter. Your pupil can constrict, get very small, or it can dilate and get larger. And we're going to see that's really critically important because those photoreceptors, they can't all be absorbing light sort of simultaneously. It's like if somebody gets a flash photograph, and it's suddenly too bright, and you close your eyes and look away because there's no information in activating every photoreceptor. You want sort of selective activation, so that the light level is pretty critical to adjust to the ambient light conditions. And you can see people's pupils will dilate in darkness, and they will constrict significantly in brighter light. Actually, if you do get a flash photograph, right, if you overwhelm the retina, the photoreceptors at the back of the eye and the retina, you'll actually see this phenomenon called red eye, which is actually a reflection back, basically from blood, the blood that is actually, it's quite well vascularized at the back of the eyeball to feed those photoreceptive cells and other cells in the retina. Actually, one thing we like to tell kids in public schools is that, when you're looking around, your pupils are black because, energy is actually coming in, but it's going to get absorbed by the photoreceptors, by the pigments at the back of the eye, and it's not going to get back out. So you're really like, pulling and transducing energy, as you look around the room with your eyes. The electromagnetic radiation will continue through the pupil and then encounter a structure called the lens. And the lens is, initially, in most of us, right, quite flexible. And it can be pulled on by muscles to, kind of flatten it out or to scrunch it up. And, if you look at something close to looking at something farther away, you are altering the structure of that lens in ways that bend those light rays, that bend that electromagnetic radiation, so you can focus the image on the photoreceptive surface at the retina at the back of the eyeball. And this is a very natural process, but when you hit your late 40s, early 50s, typically, or it has been typical in past generations, that lens tends to get significantly less flexible, so it's harder to pull, and alter its structure to, bend light rays in different ways depending on what you're focusing on, how far away something is. And so this is called presbyopia, and typically people will get glasses at that point, or they'll get progressive lenses, so they have multiple focal lengths that they can then basically adjust their lens around so they can still see. There's some really interesting research that looks at like exposure to outdoor environments, particularly to sort of natural environments, going walking in forests and walking in natural areas, and how that's actually quite healthy for eye function and for lens function, and how these things may not be so helpful. In fact, the age of onset of presbyopia seems to be declining in current generations compared to past. And then finally, the light, once it's been bent by the lens, it's going to arrive back, at specific, photoreceptors that are embedded in the retina, which is located at the very, very back of the eyeball. And we'll talk about the retina next.